Welcome to the Explainer. Okay, let's jump straight into this. Imagine a high-tech, yellow and black blueprint world. But instead of sketching out skyscrapers or jet engines, we're engineering machines at literally the smallest scale imaginable, the atomic level. Today we're cracking open the blueprints for nanomachines made entirely out of single molecules.
Back in 1960, the visionary physicist Richard Feynman dropped this incredibly famous line, "There's plenty of room at the bottom." And to give you an idea of the sheer, awe-inspiring scale he was talking about, he envisioned writing the entire Encyclopedia Britannica on the head of a pin. He was laying down the ultimate engineering challenge. For decades, it was just this theoretical dream. But today, we are actually building controllable, autonomous motors out of individual molecules. It's a massive leap from science fiction to scientific reality.
So, here's our blueprint for today's Explainer. We'll meet the molecular motor, figure out how to fuel these nano engines, compare nature versus synthetic designs, look at cross-pollinating the sciences, and finally, dive into the future of nanomachines. Let's get to it.
Section 1. Meet the molecular motor, engineering the invisible.
To really wrap your head around a molecular motor, you've kind of got to throw out everything you know about a car engine. The physics down at the nanoscale are just fundamentally different. These motors operate in what physicists call low Reynolds number and overdamped conditions. Basically, if you were a molecular motor, your environment wouldn't feel like thin air. It would feel like trying to swim through extremely thick molasses. And it gets worse. You're in this chaotic thermal bath, constantly being pelted by the random, violent collisions of surrounding molecules. It's called Brownian motion. Imagine swimming in molasses while being pelted by boulders. You absolutely cannot rely on momentum here. The split second you stop applying force, you stop moving. Period.
Section 2. Fueling the nano engine, thermodynamics at play.
So how exactly do you move in molasses while being pelted by boulders? We have to zoom in on the thermodynamics, specifically how we use chemical potential and fuel decomposition to drive these systems out of equilibrium. And to really understand motor performance, we have to look at the thermodynamic uncertainty relation, or TUR. Think of the TUR as the ultimate thermodynamic speed limit. It's this fundamental physics inequality that tells us just how precisely and efficiently a fluctuating macroscopic system can operate based on the energy it dissipates. It literally defines the absolute ceiling for a motor's performance.
But here's the thing. Artificial motors rarely hit this speed limit. The crucial question is why? Researchers have pinned down 4 physical parameters that act like a diagnostic checklist for engine inefficiency. If your motor is underperforming, it generally comes down to the thermodynamic driving force, the rate at which fuel breaks down, how tightly that fuel decomposition is coupled to actual movement, and how much the motor randomly jiggles around without even being driven.
Take a look at this simulated artificial Catanian motor. See that green ring shuttling around the larger black ring? When scientists map its current fluctuations, they find it deviates wildly from the optimal TUR bound. You can see that in the graphs on the right. Why is that? Well, it's primarily due to a lack of tight mechanical coupling. The fuel breaks down, sure, but that energy isn't efficiently forcing the ring to move. A huge chunk of it is just wasted as heat in the chemical bath.
Still, despite those inefficiencies, continuous motion is possible. Notice this beautifully simple ABC chemical transformation cycle. By constantly breaking down a chemical fuel, we push the molecule from state A to B to C, effectively creating a one-way street. It's this continuous flow of chemical energy moving the system far out of equilibrium that forces the motor into an autonomous unidirectional spin. It's pretty amazing. Which leads us to Section 3. Nature versus synthetic designs. The microengineering conflict.
We are currently trying to build what nature has been perfecting for literally billions of years. Let's compare biology's legacy with our brand new synthetic designs. On the left, we have nature. Biological motors like the myosin in your muscles or ATP synthase are just absolute marvels of engineering. They're highly efficient, perfectly unidirectional, and feature incredibly tight mechanical coupling. That means almost every piece of fuel directly results in a mechanical step. Now on the right, look at our synthetic motors like rotaxanes and catenanes. They're brilliant human achievements for sure, but right now they suffer from low efficiency and loose coupling. We're very much at an early stage of performance here.
Just to put a number on this gap, biological motors operate orders of magnitude closer to the turbound. We're talking about a staggering efficiency gap. Biological motors are driving right up near that thermodynamic speed limit. Our current artificial Catanian motors, they deviate from that limit by 5 to 6 orders of magnitude. It's like we're stuck in the slow lane on a bicycle and biology is just cruising right past us on the Autobahn.
Now you might be wondering, well, why do we even bother building synthetic motors if biology is just so much better at it? It turns out synthetic designs offer massive advantages. You see, biological motors are incredibly fragile. They really only work in very specific, watery environments inside a living cell. But with synthetic motors, we can design them entirely from scratch. We can make them physically and thermally stable, we can power them with light or electricity, not just chemical fuel, and most importantly, we can deploy them outside of living organisms to do actual work in the real world.
All right, Section 4, Cross-Pollinating the Sciences, Merging Disciplines. So, to harness the durability of synthetic designs and the insane efficiency of biological ones, we have to look at the broader scientific landscape. The multi-million-dollar question is this: how do we bridge the massive gap between biological perfection and synthetic potential? Because historically, biologists, chemists, and physicists have mostly been working on completely independent tracks.
The roadmap to solving this is actually beautifully laid out by the Japanese Molecular Engine project. It's this huge collaborative effort. The idea is simple but powerful. We need physics to understand the fundamental laws, chemistry to actually build the structures, and biology to learn from existing natural masterpieces. Let's break that strategy down into actionable steps. Step 1. We look to biology to learn the rules of tight coupling, how to make absolutely sure fuel directly translates to motion. Step 2. We use physics to calculate our fundamental thermodynamic limits, so we know exactly what's theoretically possible. And Step 3. We rely on chemistry to synthesize these entirely new, robust architectures from the ground up. It's basically the ultimate interdisciplinary tag team.
And that brings us to our final leg, Section 5, the future of nanomachines, building the impossible. If we can actually nail this thermodynamic engineering, the breakthroughs waiting for us are just, well, they're mind-bending. The ultimate hurdle we're facing right now is moving from individual molecular switches just thrashing around in a chemical bath to creating collective, synchronized assemblies. We need billions of these nanoscale motors all pushing and pulling together to perform measurable, macroscopic work. It's exactly how the billions of tiny myosin motors in your arm allow you to lift a heavy weight.
And once we achieve that, the applications are incredible. We already have early prototypes of molecular robots that can actually grasp and connect amino acids together, kind of like microscopic assembly line workers. Researchers are even developing molecular motors attached to long polymers. When you hit them with light, the motors wind the polymers into tight, messy bundles, literally storing light energy as mechanical tension. It's a completely new type of battery. We're also looking at hybrid micro-electromechanical systems and even artificial cells that act as complex, compartmentalized chemical factories right there at the nanoscale.
We are literally standing at the absolute frontier of a nanotech revolution. We've learned how they move, how they're fueled, and how to combine the best of nature with synthetic chemistry. So I'll leave you with this final provocative thought to take away from this explainer today. Once we've fully mastered the blueprints of the invisible world, what macroscopic tasks will these invisible nano-engines eventually conquer for humanity? The possibilities really are as limitless as the atomic world itself. Thanks for joining me on this explainer, and as always, keep questioning the world around you.